Welcome to The Explainer. Today we're taking a deep dive into the human brain to explore the incredible science behind medications for psychosis. It's really a story about progress, about moving from something like a chemical sledgehammer to a finely tuned orchestra, all to bring a little harmony back to the mind. So, let's get into it. And this, right here, is the million-dollar question. It's the puzzle that neuroscientists have been trying to solve for decades. Think about it. How do you turn down just one really loud conversation in a packed stadium without making the entire stadium go silent? That's the challenge, and that's the story we're going to unpack today.
So here's how we're going to break it all down. We'll start with the absolute basics, the brain's chemical signals. Then, we'll walk through the history, from those first powerful but blunt instruments to the idea of tuning the orchestra and even completely rewriting the musical score. From there, we'll get into the personal side of things, genetics, before we look ahead to the future of treatment.
All right, so to really get how these drugs work, we need to understand two key concepts. You can think of them as two sides of the very same coin, and they control everything from how well a drug works to the side effects it might cause.
First up, we've got pharmacokinetics. Now, the easy way to remember this is it's what your body does to the drug. It's the whole journey, how your body absorbs it, where it sends it, how it breaks it down, and finally, how it gets rid of it. It's all about your body's own unique processing plant.
And the other side of that coin is pharmacodynamics. This is what the drug does to your body. This is the action part. This is where the rubber meets the road. It's like the key fitting perfectly into a lock to make something happen. This is how the medicine actually produces its therapeutic effect and, yeah, its side effects too. You really have to understand both.
Okay, now that we've got that down, let's rewind the clock and go back to the very first generation of these medications. They were absolutely revolutionary for their time, but as you're about to see, they were also incredibly powerful, blunt instruments.
So early on, scientists figured out that a lot of symptoms were tied to an overactivity of a chemical called dopamine in certain parts of the brain. They even had a fancy name for it, hyperdopaminergia, which really just means too much dopamine. So the logic was pretty straightforward. If there's too much signal, let's just block the receivers, in this case, the dopamine D2 receptors. The goal was simple, turn down the volume.
And you know what? It worked. It really did help ease those positive symptoms. But, and this is a huge but, there was a major trade-off. The problem was that these drugs weren't selective at all. They were like a shotgun, not a sniper rifle. They blocked those D2 receptors everywhere in the brain, not just where they needed to.
And that non-selective blocking had some really serious consequences. For instance, when you block dopamine in the part of the brain that controls movement, well, you get these severe motor side effects. Or if you block it in the pathway that handles cognition, you can actually make other symptoms like apathy even worse. And in another pathway, it just completely threw hormones out of whack. This was the unfortunate cost of doing business with that first generation of drugs.
So the next great leap forward wasn't about hitting that dopamine receptor harder. No, it was about getting smarter. It was about learning how to tune the orchestra. And they did that by adding a whole new instrument to the mix, serotonin.
And this is where things get really clever. Researchers figured out that if they also blocked a specific serotonin receptor called 5-HT2A, they could actually increase dopamine in the very same places where the first-generation drugs were causing all the problems. It was like finding a backdoor way to fix the issues that the front door approach was creating, all while keeping that therapeutic benefit.
This whole idea led to an even more elegant solution. What if, instead of just a clunky on-off switch for dopamine, you could have a dimmer switch, something with a bit more finesse that could modulate the whole system? And that is the absolute magic of what we call partial agonists. You might have heard of drugs known as the PIPs and the RIP. What they do is they bind to that D2 receptor, but they only turn it on part way, say to about 50%. So in a part of the brain with way too much dopamine, they get in the way and turn the volume down. But in a part with too little dopamine, they give it a gentle nudge and turn the volume up. It's a stabilizing effect, and it leads to way fewer motor and hormonal side effects.
But the story doesn't stop there. Tuning the orchestra is one thing. The latest generation of drugs? Well, they're doing something even more radical. They're basically rewriting the musical score from scratch, finding entirely new harmonies to bring balance to the brain. Okay, check this out. Take a drug like lumateperone. Its strategy is just brilliant. Instead of only blocking dopamine where it's received, it goes right to the source. It acts on the presynaptic receptors, the little gatekeepers that decide how much dopamine gets released in the first place. So by turning down the flow at the source, you need way less blockade at the destination. The bottom line? You get the same great results, but with a much, much lower risk of side effects.
And now we're right at the cutting edge with a new class of drugs called TAR1 agonists. What's so wild about these is they don't block the D2 receptor at all, not even a little bit. They work on a completely different system that just kind of nudges dopamine activity indirectly. This is a massive paradigm shift. It's a way to find that balance that completely sidesteps the old problems tied to the D2 receptor.
So, we've talked a lot about what the drug does to the body. That's pharmacodynamics. But now we got to flip that coin back over and talk about what the body does to the drug. This is what we call the personal equation. So let me introduce you to your body's personal engine for drug processing, a family of liver enzymes called CYP450. Think of these as the workers on an assembly line, breaking down medications so your body can use them and then get rid of them. And here's the kicker. The instruction manual for how well your personal assembly line runs is literally written in your DNA.
And this chart just lays it out perfectly. See, most people are what we call extensive metabolizers. That's the normal group. And standard drug doses are designed for them. But some people are poor metabolizers. Their enzyme assembly line is slow, so the drug builds up in their system, increasing the risk of side effects. On the flip side, you have ultra-rapid metabolizers. Their enzymes are in overdrive, clearing the drug so fast it barely has time to work. This is exactly why personalized medicine is so incredibly important.
So where does this whole journey leave us? Well, we've gone from a single, loud, blunt instrument to a full, dynamic orchestra. And the future is all about making that music even more personal and even more precise.
You know, there's a quote from the source material for this that just captures the entire story perfectly. It says that older drugs had one instrument, modern drugs added more instruments, and these newest agents are finding entirely new harmonies. That just nails it. It's a story of ever-increasing sophistication.
Of course, the work isn't done, not by a long shot. There's still major challenges, especially with managing side effects like weight gain and other metabolic issues. The ultimate goal here, the holy grail really, is to get away from trial and error completely and get to a point where a simple genetic test can tell a doctor exactly which drug at exactly which dose is perfect for each person, right from day one.
And that leaves us with one last thought. We have mapped so much of the brain's incredible, intricate music. But you just know there are still hidden melodies and unheard harmonies just waiting for us to find them. The question isn't if we'll discover them, but when. Thanks for digging into this with us.